Hello everyone, welcome to ECE 209 Winter 2021 Labs. In this video we will cover lab number 4, which is on phasors and AC power. So in this lab we will be continuing using the equipment and components that we used in the last lab, and we will be focusing on AC circuits, and we will validate the AC circuit theory in this lab that you would have already learned in your lectures. So equipment will remain the same that we used in the previous lab, and you will be introduced to the following concepts, which are phasors, um, active, reactive, and apparent power, power factor, power triangle, RLC series circuit, and RC parallel circuit. And you will be needing a few components such as 10 ohms resistor, 470 ohm, 1 kilo ohm, 2.2 kilo ohm, 100 nanofarad capacitor, 220 nanofarad capacitor, and a 10 millihenry inductor. You can read more on the backgrounds of each of the topic. So in terms of procedure, let's look at the first one, in which we will be using the scope to measure the phase, and we will use the cursor on the scope to measure the relative phase between two signals. So let's connect our analog discovery 2. Alright, so open the waveform program and make sure that it's successfully connected. Connect the WaveGen1 output to the channel 1. So let's connect it on our board. So we will connect 1 plus to W1, and 1 minus to ground, and 2 plus to W2, and 2 minus to ground. Alright, so this is how your circuit will look like. Um, you just need to connect the wires. Alright, once you have the connection, you will go to your waveform. Using the waveform tool, create two sine waveforms both at 1 kilohertz. So we will use waveform and generate sine wave both at 1 kilohertz. So This will be for channel number 1, and for channel number 2. So we will go to this channels bar and activate channel number 2 as well. And channel number 2 should also have same values. Double check that both channels are currently configured like the following. Okay, 1 kilohertz, 1 volts. Sorry, the amplitude should be 1 volts. Offsets should be 0. Alright. Next, in channel number 2, we will change the phase to 90 degrees. So we will go to channel number 2 and make the phase to 90 degrees. Let's make this symmetric, evenly distributed, and then in the top toolbar, in the drop down to the right of the channels drop down, you will also need to select synchronize as shown below. So here in the synchronization, we will select the synchronized, and then we will click on run all. Alright, so now both are running. Now with the wavegen running, also open up the scope tool in the waveform and click on the run button. So we will now bring in scope, and in the scope we will press the run button. You should be able to see two wavegen outputs being measured on the scope display. Alright, so we should have actually we have math from the previous lab. I've deleted it now, and we need to enable channel number 2. So now I've enabled it. We will change volts per division, same for each, and then we can decrease the base to 200, or rather 100. Oh yeah, 100 microseconds per division. Alright, once we have this, you can see that the blue is currently leading, because you see its high comes before the high of yellow one. So blue is leading and yellow is lagging. To measure the phase difference between the two waveforms in time, we can easily approximate this by counting the horizontal divisions from where the yellow crosses the 0 level to where the blue crosses the 0 level. So we can see, okay, where the blue is crossing 0 level and where the yellow is crossing 0 level. You can see it's crossing here in the center of these two divisions, in the center of this box, which is 2.5 divisions, and we know the divisions we've set to 100 microsecond per division. So we can use these values to determine the phase difference between both. This is about 2.5 divisions with a base of 100 microsecond per division. That works out to be 250 microsecond. And that the frequency of this waveform is 1 kilohertz. The period is 1000 microseconds. So to solve for the phase difference in degrees, you simply need to take the measured 250 microsecond and divide by the period, and then multiply by 360. So you can follow these steps. When doing so, you will notice 90 degrees of phase difference, which is the same as the angle we put in to the channel 2 wavegen signal. Alright, as the number of divisions don't always work out so nicely as the example, you can either use the X cursor tool located in the top toolbar or the quick measure tool that we are going to show here to make a quicker, more accurate measurement. To activate the tool, simply double click anywhere in the scopes waveform display and your cursor will become a vertical red bar. So if we double click anywhere, we can simply use the cursor, just double click somewhere. You can move around the display like the one shown below. Click somewhere else and it will move, or if you click and drag, then it will start showing the difference. Alright, when you move the red cursor left and right on the display, it will tell you the instantaneous voltages, the voltage of both channels at the specific time. So if you move, you will see C1 is showing me the voltage for channel 1, C2 is showing the voltage for channel 2, and X is showing the time. And when you move the red cursor left or right on the display, it will tell you instantaneous voltage. First, find the closest time when the blue waveform is closest to 0. So suppose this is where it's almost 0, and click the mouse button. Now, second, move the cursor to the closest time when the yellow is close to 0. So this is when the yellow is close to 0. We will look at C1, channel number 1, when it's changing between positive and negative. That's the point where it's close to 0. Now we will click mouse again. Alright, let's close the measurements tab. Okay, so the display should look like similar. There's now a lot of information on the screen, but the value that we are interested in is the delta x. So you see there are so many values: delta, delta x, 1 over delta x, and delta by delta x. So we are interested in delta x at this point. Which is the time between the two red cursors on the display above. This time is measured at 250 microseconds. Yes, in my case it's around 249.3 microseconds, which closely matches what we measured when we simply counted the divisions. Below is the equation which turns this measured time into phase value. So you can use the phase divided by period into 360 degrees to get the phase difference. Alright, when measuring the phase in time between two waveforms, it's important to measure the time starting with the reference waveform to the waveform under test to obtain the correct sign. So as we initially identified that blue is leading and yellow is lagging. So if we wanted to see the phase difference between blue and yellow and the delay of yellow waveform, then our reference will be blue. So we will start from blue and then measure the yellow one. So blue one is reference. So if the reference waveform is to the right of the waveform under test, it is said to be leading, and the sign will be negative. If the waveform under test is lagging, then the sign will be positive. So in our case, the yellow is lagging. Alright, so in the following ones, you will introduce individual components and then determine phase, lead and lag in different situations. So in the first one you have resistors. We will simply connect two resistors in series. Channel 1 will be connected across R1, channel 2 across R2. So use the circuit below to measure both the voltage across the current through the K1 resistor on the scope to see the phasor relationship between the two. Also use the scope to calculate the instantaneous power through the resistor. So we are using a small resistor here which will help us determine the current flowing through the circuit, which is our sense. So as you can read here that this is a current sense resistor and it's a small value, and we simply use it to determine the current flowing through the circuit. Alright, let's build the circuit. So I will show you how this circuit will look like, and then you will simply follow the steps given in the lab manual to get all the readings. So we need 1 kilo ohm and 10 ohm resistor. Alright, so here is the 1 kilo ohm resistor, and we need 10 ohms. Okay, here is the 10 ohm resistor. Alright, so let's insert 1 kilo ohm resistor in series with 10 ohm resistor. Like this. And then we will connect W1 W1 to R1 and the other end to the ground. And channel 1 will go across R1. So channel 1 will be connected across R1. So 1 plus will be connected to the first end and 1 minus will be connected to the other end of the resistor, and channel 2 will be connected to one end of the resistor and 2 minus will be connected to the other end like this. Alright, once you have everything connected, use W1 as an AC voltage source to supply a 5 volt peak sine wave at 5 kHz across the resistor. So we will go to our waveform and let's stop it. Change the frequency to 5 kilohertz, amplitude to 5 volts peak. Use the two scopes channels. Let's turn this on. Although we don't need channel 2 W2 at this moment. Let's go back to oscilloscope and use the two scope channels to measure the voltage across R1 and to measure voltage across R sense. Alright, and run the WaveGen tool in waveforms to enable the AC voltage source and use the scope tool to display the voltage across each resistor at an appropriate scale. So let's change the scales. Channel 2 is currently very small, so let's amplify it a bit and reduce channel 1 2 volts peak to peak, 2 volts per division. Okay, what's happening? Why? This resistor is not connected properly, that's why everything is shaking. Now it's fine. Alright. For the current sense resistor voltage measured on channel 2, create a new channel by clicking on add channel. So we will go to add channel and then create a new custom channel and adding the appropriate math to calculate the current. So it will be C2 divided by 10. And change the units to amperes. Click on OK and change the divisions to something bigger. Alright, so change it to 10 milliamps per division. Adjust the scale and then you can use the checkbox in channel 2 to hide it, as we're just using it as an intermediate signal to obtain the current, so you can turn off channel number 2. Alright, to obtain the instantaneous power waveform for the resistor under test 1 kilo ohm, we will multiply the voltage waveform on channel 1 by the current waveform on the new channel you created above math 1. Create this new channel by clicking on add simple and make the first term C1 the operator X and the second term math 1 is shown below. So we will create a simple channel now in which we have C1 X M1. Alright, and we will adjust the divisions to 10 millivolts per division. Just the scale for the new power waveform. So you can see in the few cycles. Use the measurement tool in the scope to add an automatic measurement for both the period and the RMS voltage for channel 1. The RMS current for your current channel math 1 and the average maximum and minimum powers for your power channel math 2. Record the measurements. So you can simply now go to measurements tab and maybe remove the previous ones if you have any, and now we will add. So we need for period, which is the horizontal axis, and RMS voltage, which is the vertical axis. The RMS current for your current, so we will click on math and then RMS, and then average, maximum and minimum powers. So average, maximum and minimum. So we now have all the values and we can record them. We use the scope measuring phase procedure from the equipment familiarization to determine the phase difference between the current through I and the voltage V. Alright, so we learned in the previous section how we can measure the phase. So we will increase this. And then we know that channel 1 is voltage, and we know that math 1 is current. So we can simply use this to measure the phase difference between the current and voltage. And of course you can easily do that using cursors. Remember, you need to look at the zero crossings and then see if there is any lead or lag between yellow and red or not. Alright, then you will replace this resistor with a capacitor, the 1K, and perform all the experiments. After that, in section 2.2.3, you will replace it with the inductor and then perform all the experiments. Then you will move to series RLC circuit. So in this one, you will simply connect your capacitor with inductor and then the resistor. And I believe by now you should be able to connect this circuit by yourself. So it shouldn't be difficult now to connect this circuit, and then follow all the steps and you will perform all the measurements for RLC, series RLC, and then in this one you have parallel RLC. So you will simply have this is 10 ohm resistor, so don't consider it anything like when you're looking at the parallel. So in this we have R in parallel with C. and these 10 ohm resistors are simply for measuring current. So I'm hoping you will be easily able to connect this circuit and perform all the experiments as given in the lab manual, and then finally um, it will be all finished. And one thing, just keep in mind that we don't have any post lab. So although in the lab manual it says about the post lab, but for this semester we don't have any post lab, so you don't need to do uh, any post lab work. Only measurements should be enough for this lab number 4. Just perform all the measurements and then just skip all the post labs. If you want to voluntarily do um, the post lab, it's easy. You just need to measure the phase, lag and lead, but it's not necessary. So any post lab work in this lab is um, excluded. You don't have to do any of it. So I believe it's an easy lab. You can easily do it. And if you have any questions or any problems in your circuit, just contact us, send an email to your TA, and they will help you solve the problems. And good luck with your exams.